Alright, hello. Today we're doing FRQ number 1. So, part A asks to find the instantaneous speed at 25 degrees below the starting point. So, first thing I would do is I'd set up PE equals KE, that's conservation of mechanical energy, equals ME. And so this is just MGH equals 1 half MV squared. And then after that, I can cancel out the M because they have the same M. So I multiply, so it'd be 2GH equals V squared. But then I would have to do H sine 25 now because I'm looking for the height that is just specifically fallen. So I would do 2G, and then H, I'll do L sine 25. That's the height that it's fallen. Equals V to the square root of that. So then now I'd plug it in, so just do radical 2, 9.8, 3 sine 25, which is V, and then plug that to a calculator, and then 4.98 meters per second. But then since they have speed, so that's just the magnitude, so that's the answer for part A. Part B is asking for the magnitude of the ball's net acceleration. So I know acceleration has two components, which is AC and A tan. So then I would find AC, which is V squared over R. And then using the answer from the last question, I know that V is 4.98 meters per second squared. The R is 3 because that's just the length of the rod, or the length of the string. And so that gives me, when I plug into a calculator, 8.28 meters per second squared. And then that's the AC, but then there's also A tan. And then A tan is equal to G, which is gravity pointing straight downward. But then I need the component pointing in the line of motion. And the angle that gives you that is cosine, because that's the angle, the angle's at the top, so it's cosine. So G cosine of 25. And then plug that into a calculator, which is 9.8 cosine 25, gives you 8.88. And then it's asking for net acceleration, so that's A total. And A total is just AC squared plus A tan squared, all under square root. So take square root of 8.28 squared plus, and then when I plug that all into the calculator, I get that A total is equal to 12.14 meters per second squared. And since it's asking for the magnitude, there's no direction, so I just put that as the answer. Alright, moving on to do part C now. It's asking to find the angular acceleration at 25 degrees below. So we know alpha is equal to A over R, but in this case it's just A tan over R. And then in the last part we found that A tan was 8.88, and then R is 3 because that's just the length of the string. And so plug into your calculator, you should get that A, or alpha, is equal to 2.96 rads per second squared. It's asking for the magnitude of the angular acceleration, so that's just the answer, no direction needed. Part D now is asking to find T at the lowest point in this swing. And so first, set net force equals Fc, which is the first part to set up. And so the force at the very bottom would just be T minus mg. T points straight up, and then mg points straight down. And then Fc can be expanded out to mv squared over r. And so we're asking for T to find it, so we just add mg over, so T is equal to squared over r plus mg. And then now we see that we're missing a v at the very bottom, so we just find that easily by setting up me equals me. And so that's just going to be pe equals ke. Just going to be like this. M's cancel again, so it's 2gh that equals v. But then that's at the very bottom now, so the height is now 3 because it's fallen the full way. So 2 and 3 equals v. Put that in your calculator. V is equal to 7.67 meters per second. So we take that number and we plug that in to find T. So T equals M. The mass was 1.8. V is 7.67 squared over R. R is 3. 1.8 for that M, and then G is 9.8 in this case. So plug that all into your calculator and you should get 52.92 newtons, which is T, asking for the magnitude, so that's no direction, so that's just the answer right there. Okay, So now we're gonna do part E. So it's asking for the velocity of the steel ball after the collision. So we're gonna set up initially momentum. Let me zoom in so we have a little bit more room. So Pi equals Pf, momentum equals momentum. So this is just mv plus mv equals mv plus mv. 1 1 2 2. This is F F. But initially m2, which I'm gonna say is the block, does not move, so it's gone. So then now I know m1 is 1.8, v1 I, which I found the last question was 7.67, and then over here 1.8 again, v1f unknown, uh, v2f, which is unknown again. And so now I have to isolate. In my work I'm gonna isolate for v2f because I'm trying to solve for v1. So 1.8 7.67 minus 1.8 v1f, and then I divide by 0.4 to get v2f. And then now I'm gonna simplify this down to make it a little easier for later. So it's just 34.515 minus 4.5 v1f equals v2f. Now we have two unknowns, and so I'm gonna set up energy now. So and this is just ke plus ke plus ke is 1 2 1 2. But then ke for the block doesn't exist initially because it's at rest. So then just 1 half m1 v1 I squared, 1 half m1 v1 f squared plus 1 half m2 v2 f squared. I'm gonna cancel out all the 1 halves to make it easier. So now I know m1 is 1.8, v1 I was 7.67. Square that. m1 1.8. We don't know that, so just keep it like that. M2 is 0.4, and then now for V2F, we know from down there or from before that this is 34.515 minus 4.5 V1F. Square that. So now I'm gonna simplify all these parts over here. So then I get that this is a 105.89 here. This stays out of 1.8 V1F squared. Now I'm gonna FOIL all this in here, so it should give me 1191.285 minus 155.32 v1f minus 155.32. That's really messy. Let me fix that. Minus 155.32 v1f plus 20.25 v1f squared. And so now I'm gonna combine the like terms and distribute the 0.4 to each term. So this is 476.523 minus 124.254 v1f plus 8.1 v1f squared. We fill in the rest of this. And so now, again, I'm going to combine like terms. I'm going to move the 105 to the right, onto the right side, so like this. So then combine like terms, 9.9 v1f squared minus 124.254 v1f plus, move it over, so this is 370.63. And so now I can quadratic formula this to find v1f. So then by doing that, I get v1f is equal to 4.88 meters per second, or I get it equal to 7.67. But then this answer does not make sense, so I'd have to choose this answer. And then it's velocity, but then the answer was positive, so it's going to the right, so it's plus. So plus 4.88 meters per second for V1F, or the steel block. That is part E. Alright, now we're going on to part F. Let me move down here. So for part F, it's asking for how much time it will take for the block to come to a stop. So the first thing I would do is I would set up net force equals ma, and since the block is only being acted upon by friction after the collision, so I'll say Fk equals ma. So then I'll expand Fk equals mg uk equals ma. M's cancel, so I get g mu k equals a. So now I can set for a, so I get 9.8 times 0.16, which is mu k was given as 0.16. 9.8 is just g equals a, and so I get that a is equal to 1.57 meters per second squared, and that's negative because it should be acting against you. So now I can set up common form to find out how far the block has traveled. So I would do Vf squared minus Vi squared equals 2a delta x. Vf is 0, so I cancel it out. So negative Vi squared. This is V2 now, so I need to find out what V2 is, the initial velocity of the block. So I can do that again by using the last problem. So I know that after the collision, the velocity of the steel ball was 4.88, and then using this equation right here, I can solve for the velocity of the block after the collision. So I get 34.515 minus 4.5 times 4.88 positive, because it's positive velocity, which means V2F. So then I put that in my calculator. I get that V2F equals 12.56 rounded. Positive again. And so now I can take that information. So I go negative squared equals 2 delta x. And so now I isolate for delta x. So I do the negatives will cancel right here. So I do 12.56 squared over 2 times 1.57. And then delta x I get as 50.2 meters. So now I want to solve for t. So then I can set up average velocity, because I know a is a constant, because the only force acting on it is f of k. But then that just that's the only force, so something else. So that's a constant. So then I can set up average velocity equals average velocity. I know average velocity for 1 equals delta x over t. But then I also know that v average can be vf plus vi over 2. That's also another way. So I can set those equal to each other. Vf is 0, so I get Vi over 2 equals delta x over t. So now I can explain everything I know. So I get 50.2 over t equals Vi. Vi was 12.56 over 2. If I want to isolate for t, I get t is equal to 2 times 50.2 divided by 12.56, which is 8 seconds. Alright, so now we're going to go into part G, which is asking to find the angular speed after the collision between the block and the now put in rod. And so first off, I want to find the speed of the block right before it hits the rod. So to do that, I'm going to set up ME equals ME. So initially there's just KE, but then at the end there's E loss, which comes from the friction, and KE. So expand that out again, so it's 1/2 M. I'm going to say the block is now M1. V1I squared equals E loss. This can be expanded out, because this is the E loss is just the work due to friction. So I just do Fk times delta x, because force times displacement equals work, and then plus 1/2 M1 V1F squared, which is V1F squared is what we're solving for. So now I can plug in values again. So I get 1/2. Actually, let me not plug in values. Let me just keep expanding. Fk, which is equal to mg mu k, and then delta x in this case is 3/4 of the original delta x plus 1/2 m1. So now I can cancel out m1, and I can even cancel out a 1/2, because down here I can make this a 2. And so now, simplify that up a little bit, I get v1 I squared equals g k 3 over 2 delta x plus v1f squared. So now, like from before, we know that v1I is 12.56 squared. I'm going to move over the g mu k, so that's just minus 9.8 times 0.16 times 3 over 2. And displacement from before we found was 50.2. Equals. And so now, square root of all of that. And so now if you plug in a calculator, you should get V1F is equal to 6.3 meters per second. But then now that's just finding the velocity. Now we need to set up angular speed to after the collision. So you do Li equals Lf. So now initially I'll just do Cpr or Cmvr equals I omega. And then this cancels out, because we're saying the block is just a point mass. So then we know m, which is 0.4, v was 6.3, and then the radius from the pivot is 2 over 3L equals I omega. But then I is the I of the block, which is just 1/3 m L squared plus the point mass now that's being added on, so it's just m, and it's being hit at 2 over 3 L squared omega. And so again, I'm gonna plug in all the numbers I know. So 0 0.4, 6.3, 2 over 3. The length of the rod is 5. 1/3. The mass of the rod is 1.1. 5 squared plus, this was 0 0.4. 2 over 3. L is 5 squared omega. And then now plug all that into your calculator and isolate for omega, and then omega you should get is 0.62 rads per second. And then it's asking for the speed, so then it's just the magnitude, so that's just the answer right there. Alright, now we're gonna go on to part H, which is asking to find out the height after the collision that the rod block system will rise to. So I'm gonna set up MEI equals MEF, and then initially it's just KE rotational, and then at the end it's just potential energy, because all it's converted to. So it's 1/2 I omega squared equals mgh, and I can expand this out. So I know it's going to be 1/3 because the pivot's at the top. M2 for the block, or for the rod, L squared, plus M1 block, 2L over 3 squared, times 0.62, because that's what the omega we found in the last part was. And then M here is M total, because it's combined together. So let's start plugging in numbers. So this is 1/2, 1/3, 1.1, 5 squared plus 0.4, 2 times 5 over 3 squared. So I'm gonna simplify this a little bit. So I'm gonna keep this over here. So it's just 1/2. The I value simplified down is 13.61, and then is all equal to h, and then you plug all that into your calculator. You should get the h equals 0.178 meters. It's how high it rises after the collision. Alright, now going on to part I, the very last part. It's asking for the angular speed, if it changes, increases, or it's unchanged if the block strikes at L over 2. So to start off, we'll set up initial angular momentum is equal to final angular momentum, and then splits up to CMVR equals I omega. Just cancel that because it's just a point mass. This is M1 V1I R equals, I'm going to expand this out. This is 1/3 M2 of the rod, L squared, plus M1 L over 2, because that's where it strikes, squared omega. And so over here, M1 is 0.4, V1 we found was 6.3, and this is just L over 2. This is equal to 1/3, 1.1, and L squared is 5 squared plus 0.4, 5 over 2 squared omega, 0.4, 6.3, 5 over 2. All of that, the I value simplified, put in the calculator, is 11.67. And then all of this on the left, simplified, is 6.3. So divide 11.67 over, you get omega is equal to 0.54 rads per second. However, the rads per second originally that we found was 0.62. And then that is much greater than that. So angular momentum, or angular speed, actually decreases, which is the answer. Thank you for watching today. I just came back from losing a tennis game. Feeling pretty good. So yeah, thank you.